Hey guys, first off, the angles are going to be a little bit weird on this one because I'm stuck to the cord, so it's going to be a little bit wonky. Sorry if you can't see too well. Also, you should have the problems up in front of you through Canvas to look at. I'm not going to write the entire problem up here because I'm lazy. I don't have any time. Sorry. So first question, we have this capacitor, and it's saying draw four equipotential surfaces that are equally spaced apart. Now the thing to be very careful about here is that first off, we're drawing four lines. So we're going to have one, two, three, four lines, which means we're going to have five gaps. Now, that doesn't make a whole lot of sense yet to some of you, I know. But if we just draw this out, let's see if I can do this right the first time. One, two, three, four lines. We now have five gaps right there. Well, the difference from negative 250 to negative 750 is negative 500, which means each of those gaps has to each be negative 100. And the point that I was getting at in this question, what I was really getting at, is that the transition from here to here, that negative 500 volts, is a smooth transition. In other words, the potential doesn't randomly go up 200 volts here, but only 50 volts there. It's a very smooth transition. So we go to negative 350 volts, negative 450 volts, negative 550 volts, negative 650 volts, and then negative 750 volts. Each of those surfaces is the exact same amount apart because they're the same distance apart. Our logic here, the way we know this, is that the electric field is the negative change in voltage divided by the distance apart. So if the distance is the same, that means the delta V is the same because the electric field everywhere in there is the same. And we know it's the same just because it's how a capacitor works. That's what happens. The electric field here is going to point from more positive to less positive voltage, or from high to low, with that number line relationship we've been stressing, where in this case, negative 750 is actually lower than negative 250. So we're going to have an electric field that points perpendicular to those equipotential surfaces. That's how it always works. And it's going to be the same spread out. Mistakes that I saw last class, people were drawing their equipotential surfaces like this. That's not how it works at all. If that's the level of understanding you're at, you need to read your textbook. You need to come talk to me ASAP, basically tomorrow morning. So that was that one. Just go on a quick field trip. Get you set up right there. That glare is not too terrible, I suppose. We have a proton that can't move and an electron at rest. Those are 10 meters apart. Now we're trying to find the delta U, the potential energy. So the challenge here is that we have lots of different ways to do that. We can say, like, these are all the equations we know that involve delta U. Delta UE is the negative change in kinetic energy. We can also say that delta UE is Q delta V. We can also say that delta UE is U final minus U initial. We have all those different ideas that we can use to get a final answer. So we need to think about what we have. We don't really have anything about potential values, which would suggest that equation. We don't have anything about a change in kinetic energy. We just know it starts from rest, but we don't know the final velocity, so we couldn't do it that way. We do, however, know about a charge, another charge, and then two different distances, which is going to suggest this, which means from here it's just a matter of plugging stuff in. The K final, we're going to have K. We're going to have the charge on a proton. We're going to have the charge on an electron. And we're going to have the final distance. Minus K times charge on a proton, charge on an electron, divided by the initial distance. When we go through and plug numbers in, the only trick we have to be careful about is, remember, the proton has a positive charge, the electron has a negative charge. That must be reflected in the numbers that we plug in. Now I'm going to erase this out of space. Obviously, you would want to include this step in your work so the grader, me, knows that you know what you're talking about. So we would say that equals K positive 1.6 times 10 to the minus 19 times negative 1.6 times 10 to the minus 19, all of that over the final distance, which in this case, if it's pulled 4 meters, is 6. And then from that, I'm still going to have to run out of room, we would subtract K, exact same thing, except now final distance, our initial distance was that original 10 meters. Now I'm expecting that you can plug all this in and you can get a final answer. If not, you have some problems you need to address real fast. You're going to plug that in, you're going to get some value. I don't care what that value is right now, honestly. That's not really a thing that is very important to me. What I care about is that you will understand the physics there. So I am going to just make up a number. I'm going to say that the change in potential energy that we got is that it lost, we'll say 50 joules of potential energy. That's an insane amount for an electron, but who cares? Part B says find the final velocity. What is the final velocity of an electron that starts at rest and then gets pulled? Well, we know that just from understanding physics, that things always happen to try and convert potential energy into other stuff. So when the electron loses that 50 joules of potential energy, it's going to turn in to kinetic energy. So we can say that the change in potential energy is the negative change in the kinetic energy, which we can then expand into negative K final minus K initial. Well, K initial is 0, so that goes away because it starts from rest. And then this becomes negative K final, so we end up with delta UE equals negative K final. This, a lot of times, you're going to have to calculate with this formula. But we already calculated it with this one. We already got a made-up answer, in fairness, but we already got an answer. Negative 50 equals negative K final. You guys are bright kids. I'm going to go ahead and plug in 1/2 in the final squared there. Notice the negatives cancel out. Just divide both sides by -1. Then go to town. You have the mass of an electron. Do some math and solve the final. All right, last one before I take a break. This is number 3. We have 3 different charges. I've labeled them A, B, and C. If they're not labeled on your paper, make them labeled. Very easy. We want to find the net potential, the net voltage, the net volts at point P. What is the net potential right there? Well, we have 3 different things creating a potential at point P, which means our net potential is going to be the potential from A plus the potential from B plus the potential from C. Not very challenging. It's actually very straightforward. The potential from A is K times QA, so 5 times 10 to the -6, divided by that distance, which is half of 6, so 3. Plus, I say plus because the negatives will just be taken care of in the wash when we plug them in. The potential from that, K 50 times 10 to the -9. Notice it's 9 because it's nano. Divided by 3 again. Plus K times this charge, QC, which is negative 10 microcoulombs. So negative 10 times 10 to the -6, all of that over that distance. And again, we are going to get some value there. I'm not actually entirely sure what that value is, and I really don't care that much. All you know is that you're going to get a number. You get some number in volts, and that is your answer. Well, then we get to what would the electric potential energy be, blah, 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 blah. You could go through and say you have that pair, and that pair, and add them all up. But that would be insane. You've already done almost all the work you need to. Because remember, our definition of electric potential energy is that it comes from a potential. This second charge is put in a spot with potential, so it has electric potential energy right there. That's awesome. That's so nice, because we already have the potential right there. We have that potential, we have the charge, so it's going to be 16 times 10 to the -6, which is that number, times that number equals some number in joules. Voila, that's the whole thing. Be right back. Okay, back again with number 4 and number 5. We've got a capacitor here. All we know about this capacitor, we have a high plate and a low plate in terms of potential. They are 300 volts apart and physically 2 millimeters apart. And our first task is to think about the electric field. Well, the first thing we can do is think about the direction. Electric fields always point from higher potential to lower potential when we use our number line logic. So we know the electric field is going to go in that direction. It's going to go left. The way we can find the magnitude is, again, that same equation we used like 2 or 3 problems ago or whatever. The electric field comes from a change in potential. The change in potential is what creates the field. Because remember, stuff is always trying to get pushed down a field, down a potential. Because normally, stuff that goes to a lower potential will have a lower potential energy, and stuff is always trying to go to a lower potential energy. So if I let this go, the gravitational field points down to push it down, because down there has lower gravitational potential, which means this marker has lower gravitational potential energy. So that delta V, we know. That distance, we know, 300 divided by 0.002. So 150, 1500, 15,000, 150,000. And we can write that as volts per meter or newtons per coulomb. It's the same unit either way. Now we want to find the acceleration of an electron inside this electric field. Well, we think back to our chains of logic. Is this an energy question or is this a force question? Well, energy doesn't really tell you acceleration ever. Force, however, does. Electric field creates an electric force on a separate charge. That separate charge feels an acceleration. So we can say F equals ma, duh. This is an electric force and only an electric force. So a charge that's placed inside an electric field will feel a force from that electric field, the magnitude of which is given by Q times E. So all I'm doing there is using F equals QE. You will need to have that formula at your beck and call tomorrow. We then rearrange this. We say that A equals QE divided by M. Go ahead and get that down. Pause if you need to. I'm going to erase. So A is 1.6 times 10 to the minus 19. That's the charge of an electron. Remember that for forces, it's always positive. So that times the electric field that we found right here, divided by the mass of an electron, which you would get off of your formula sheet. You would do that, you would get some number, you would actually know your acceleration. Now we find the final velocity. This is a kinematics problem, way back from AP Physics 1. So we have to make our list of things that we know so we can pick the right equation to use. We know that it starts from rest, so V naught is 0. We know the delta x that it's going to cover is 2 millimeters, so 0.002. And we also know the acceleration because we just found it. So we know that, we know that, we know that. We're trying to find the final velocity. We don't have anything about time in that equation, so we're going to say V final squared equals V naught squared plus 2a delta x. Plug and chug, solve for V final. I know I'm not doing numbers. I know that makes you crazy, especially you, Kyler. Sorry. Solve the numbers, understand how to do it. If you're not getting an answer that seems reasonable, then come see me. We'll work it out. We'll figure out what you're doing. You might want to consider taking a picture of what you're putting into your calculator. That way I can tell you, hey, you're making this mistake. So, moving on to the next part, number 5. Same exact problem, but now we're forced to use energy. Well, first it wants us to use the energy to predict the motion. We kind of already did that with the marker thing. Remember that our fundamental rule of how energy works, or what it does, is that things anywhere in the universe will try to get to a lower potential energy. They don't like being in those weird, unstable positions. They want to be down lower, where it's better, more stable. So the reason that this marker falls down then is because down there has lower potential energy for the marker. But let's remember, electrons are weird. They're negative. And so up here, this has higher potential, but an electron is negative, which reverses the effect. So a higher potential actually means for the electron that it has a more negative potential energy. Because remember, the things you plug into the formulas for potential energy, you plug in the negatives, which means that's going to be negative 1.6 times 10 to the minus 19 times a number. And the bigger that V gets, in other words, from here to something 300 volts bigger, the bigger that gets, the more negative the potential energy gets. So from the electron standpoint, it's like, awesome, that way's great, because that way has lower potential energy, and I like that. I like going to the place that has lower potential energy. So I'm going to go there, just like the marker wants to fall down. I know I keep coming back to this analogy, but if this marker had negative mass, it would fall up, because the negative reverses the normal way to do it. The electron would want to go this way. He'd want to go left. The electron likes over here because over there is a lower potential, which means a lower potential energy, a lower positive potential energy. The electron is the exact opposite. It wants to go to the more negative potential energy, and it needs a high number to do that, a high voltage. So electrons fall against the electric field. They go against that field. That's our answer to that one. I would expect, I promise you I'm going to put something like that on the test, but you have to use words to explain that to me. Be ready for that. The work done by the capacitor is the energy that the capacitor is giving to the electron. So we could actually write this just like that. We could add another step in and just make sure we understand that the work done by the capacitor is the change in the electron's potential energy. The capacitor is doing work, sucking potential energy out of the electron and turning it into potential energy, which means we need a little negative right there. Think about that. Make sure you understand that. The work done by that capacitor is removing potential energy and converting it into kinetic energy, which means it's sucking energy out of it. That's going to be negative. So we get to this formula. Well, we have both of those things. This is 300. This is 1.6 times 10, negative 1.6 times 10 to the minus 19. So we're going to end up plugging in negative 1.6 times 10 to the minus 19 times a positive 300 volts. And we end up for a work done by the capacitor of some number, again, I'm sorry, but who cares what, that's positive. It's a positive value. The reason it's positive is, remember, like I said, the capacitor is giving energy, giving kinetic energy to that electron. Just like if I let go of this poor marker that keeps falling, gravity is giving energy to that. Its energy is increasing. It's increasing its kinetic energy, so the work done is positive. Well, now, since we just got this answer, that's the change in the energy. That is what's happening to the energy of that electron. So when we see velocity in terms of energy, we know this is going to be conservation. Delta UE equals negative, done that every single time today, delta K. This is a number that we found, and that is equal to negative K final minus K initial. As usual, it starts from rest. That goes away. That negative, I skipped a step that I need to talk about. This logic up here, the work done by the capacitor is the negative potential energy. That means when we plug this in, it's the same magnitude, but we're going to need to throw a negative in there because the potential energy went down. The delta UE went down. If it makes you feel more comfortable, which I think a lot of you probably will, I want you to pretend that none of that happened. Ignore everything that just happened, and instead, we're just going to do this. Delta UE equals the opposite of the change in kinetic energy. This, Q delta V, this, something you've seen again and again, that's going to go away. And then when we plug numbers in, this becomes negative 1.6 times 10 to the minus 19 times 300 volts equals negative 1/2 mV final squared. The negatives will cancel out, and you can solve for V final. When you go through and do this, you're going to get the exact same answer as you should have for that kinematics equation over there. If not, you're doing something a little bit wrong. Now, unfortunately, I have to go. I don't have enough time to do this. I've got to eat dinner and then go to a volleyball game. So I'm going to try and get this up to YouTube as soon as I can. I am very sorry if it's not up on time. That's life. You'll be okay. Do what you can. Come in tomorrow morning if you have questions. I will either be in my room or I'll be at morning duty outside the library so you can get to me without a pass. I will see you then. See you tomorrow. Go Step.